For the last speaker of the conference, we have Alessandro Scagliotti from the University of Residual, I guess it's pronounced.
SISSA.
SISSA, yeah, SISSA. Oh yeah, I was reading there. Okay, so he will talk us about the optimal control approach to normalizing flow. And
okay, thank you very much for the introduction, and let me thank once again the organizers, both for the invitation and for setting up this very interesting, very exciting conference. Okay, so let's talk about business. I'm going to talk about an optimal control approach to normalizing flows. Okay, so in the very first part of this presentation, we will deal with the interplay between residual neural networks and control theory. So we will try to understand why we can use control systems to model or to provide a mathematical understanding of residual neural networks. Then we will see the interplay between the notion of network expressivity or expressivity of the neural network and the notion of system controllability. And then we will see in this framework that the training of the ResNet can be seen as the resolution of a proper optimal control problem. And finally, we will tackle the problem of normalizing flows. Okay, so what is a residual neural network in this framework, in these notations? So for me, a residual neural network is a mapping of phi from Rn to Rn, which is given as the composition of capital N elementary mappings. Each of these mapping has a very particular structure, so for each k, we have that the kth layer, if you use the common language of machine learners, is given as the sum of the identity function plus a function f that depends on the state and on a parameter uk. Okay, so the function capital F is assigned, and together with the number capital N of the layers is part of the ResNet architecture. On the other hand, the parameters u1, un, or the weights, should be properly set or learned during the so-called training process. Okay, so this kind of architectures, as I said, are called residual neural networks. Okay, so what's the connection between these ones and control systems? Well, the fact is that if we look at a layer, a single layer of a ResNet, we immediately realize that it looks as an explicit order discretization of a control system. Okay, what is a control system? A control system is nothing but an ODE in which the right-hand side depends on a parameter u that instant by instant should be specified by the user. Okay, so if we take this ordinary differential equation and we discretize it with an explicit order scheme with the step size equal to 1, we exactly obtain a layer of the ResNet. Okay, this very simple observation, but fundamental, was made independently in 2017 by Hubbard and Rutot and by Wen and An. And essentially bridges the word of residual neural networks with the word of control theory. Let me say with the well-established word of optimal control theory. Okay, so let's explore this parallelism more in depth. So in the ResNet, essentially the time is discrete and corresponds to the layers of the network. On the other hand, in the control system, we are dealing with a continuous time dynamical model, and thence the time is continuous and takes value on a compact interval. Moreover, the key ingredient of the ResNet, as we have already said, is the layers, are the elementary mappings, which have the form that we have already described, while in the control system, the key ingredient is the controlled or the parametric dynamical model. Okay, in the ResNet, for each layer, we have to specify the values of the parameters, and essentially, in the control systems, for each instant, we have to specify the value of the controller. Okay, and let me say that we usually require the controls to have some embedded irregularity, sometimes also further irregularities such as Sobolev, but common choices are L2 or L infinity. Okay, once we have set the functional space, we call the controls that belong to this space the space of admissible controls. Okay, finally, what is the object of interest? So in the ResNet, it is the composition of all these elementary mappings, while in the control system, the object of interest is the flow induced by the system. Okay? While the flow, so once we have set an admissible control, our control system actually becomes a normal ODE. And we know that to have an ODE, we can associate the flow in the phase space. Okay, let me stress an important point. So we are not interested in the full movie of the evolution, but we are interested in the final snapshot. As well as in the ResNet, we are not interested in the intermediate composition, but only in the final in the whole composition. Okay, so what are the consequences of this parallelism? So the notion of expressivity of the network is strictly linked to the notion of controllability of the system. I'm going to introduce the notion of controllability of the system in a few slides. And the process of training the network is strictly linked to the resolution of a proper optimal control problem. Okay, so from now on, we are interested in the task of diffeomorphism approximation. Okay, why diffeomorphisms? Because the flows produced by a system by choosing different controls are themselves a diffeomorphism. So the idea is that, we would like that the diffeomorphisms that we can produce through our control system by choosing different controls is rich enough. What does it mean, rich enough? It means that it has nice approximating properties in the space of the whole diffeomorphisms. Okay, if it is actually the case, then our ResNet will automatically inherit this expressivity, because the ResNet is as expressive as the control system up to the discretization error introduced by the explicit ResNet. Okay, let me say something about more complicated tasks, because in real life we do not approximate diffeomorphisms. Actually, ResNets are maybe included in larger architectures that in general will further enrich the expressivity. So we are now focused on this academic problem in order to better understand this portion of real-world architectures. Okay, so before proceeding, let me say something about popular form of residual neural networks. Okay, usually they have the following form. So they have the identity function, which is always present and is the key point in this kind of ResNets, of nets, and plus this term. In this case, S is an n times n matrix that multiplies the output of nonlinearity. Sigma is a nonlinearity that basically provides, that acts on an affine transformation of the input. Okay, let me just stress that this ResNet is highly nonlinear with respect to the parameters WK and DK. Okay, so the first explored control systems had essentially the same form. So are given as, essentially the form is exactly the same. The main difference is that many authors consider a scalar control S in front of sigma instead of a matrix value control, but it's a minor issue. Okay, let me stress once again that these systems are nonlinear with respect to the controls W and V. Okay. Okay, what about the expressivity? So in 2020, Tawad and Gavisik proved that this kind of control systems produces flow that can approximate monotone real analytic functions from Rn to Rn. Okay, so now I'm introducing you the control systems and then the ResNets that I've considered. Okay, what is the main difference with respect to the previous control system is that this one is linear with respect to the controls. Okay, I stress on the fact that the vector fields Fi are non-linear. So the control system is non-linear in the state, but is linear in the control variables. Essentially, you can imagine this control system as the superposition of m different vector fields, and instant by instant, the controls are the coefficient of a linear combination of these. Okay, we can also use this abridged notation in which F is a matrix that collects the vector fields, in which the columns are the vector fields. Okay, so why we should consider linear control systems? Okay, of course they are simpler, but is there any good reason to do that? Okay, the first insight was provided by Algachov and Savichev. Algachov is my supervisor in SISSA, and the idea is this one. Okay, let's consider two mapping to diffeomorphism phi1 and phi2 that are close to the identity. Okay, in our framework, they can be thought as two consecutive layers in the ResNet. Okay, if they are close to the identity, they can be represented as flows of two proper vector fields, F1 and F2. Okay, good. So what about their composition? Okay, the composition of these two consecutive layers can be seen, of course, as the composition of these two flows. And this one, this last one, is approximately, this is not an equality, is approximately equal to the flow generated by the superposition of the two vector fields. Okay, this is the first insight this is the first reason why considering linear control system could be could lead to anyway expressive control systems. Okay, and a posteriori motivation. Okay, this is not this is just a risk. This is not a mathematical proof, of course. And a posteriori motivation is this one: is that we can keep the space of admissible controls with the weak topology. And if we consider L2 weakly convergent sequences of admissible controls, we end up with strongly convergent flows with respect to the C0 norm on compact sets. This is theoretically, for what I have seen, the main stronger reason. This is no more the case if you are nonlinear with respect to the control. This last statement is completely false. Okay, so now I'm introducing the controllability. Okay, we are dealing with a linear control system, and all what I'm going to tell you was obtained between 2019 and 2020 by Arenzano and Scagliotti. Okay, so the vector fields F1, Fm should satisfy a technical assumption that I'm not going to talk about. I'm just telling you that this technical assumption could be satisfied, so it's not empty, by if you just include among the controlled vector fields this family. Okay, so we can assume that we are controlling among the family of controlled vector fields F1, Fm. There are these ones. Okay. So, coming back to us, we have our linear control system. On the time interval 0,1, we can, without loss of generality, work on the compact interval 0,1. And we can use phi u to denote the flow corresponding to an admissible control u. Okay, what is a controllability problem? So, given a point x1 in Rn, which is the so-called starting point, and a target point y1, we would like to find an admissible control, if exists, such that the corresponding flow maps the initial point onto the target point. Okay? This question is actually very classical, and also the answer to this question is classical as well. So you can do this job, provided that the family of vector fields is Lie bracket generating at each point. What does it mean? Not important. It's just important to say that this condition is implied by our technical assumption that we assume that it is holding. Okay, now we are dealing with a much more complicated controllability notion. Okay, same framework as before, but what happens? We are talking about ensemble controllability. So for every m, we consider an ensemble of initial particles x1, xm, and an ensemble of target particles y1, ym. These are all different from each other. Okay. The problem now is to find an admissible control u bar such that the corresponding flow maps each initial point onto the corresponding target point. Of course, this is a much harder task than before because all these identity must hold simultaneously. Okay, and of course, the larger is m, the harder is this controllability task. Okay, what is the sufficient condition for ensemble controllability? This time is exactly the Lie standard approximating property. That is our technical assumption. Okay, so in order to wrap up, we have that this technical condition implies exact controllability for finite ensembles. So given an initial Taylor point, we can map, and a target Taylor point, we can map each element of the first set onto the corresponding element of the target set. Actually, we have something more, which is exactly the expressivity result that we were looking for, that they were looking for, actually. Given a diffeomorphism psi diffeotopic to the identity, what happens? It happens that for every compact set K and for every epsilon, there exists an admissible control such that the corresponding flow provides an epsilon approximation of that diffeomorphism on the compact set K. Okay, good. What does it mean diffeotopic to the identity? It means that it can be realized as a flow of a dynamical system. So in other words, with a proper choice of an admissible control, we can replicate the action, the final time action, this is important, of any other dynamical system. Okay, this is exactly the motivation that we were looking for, and so now we just need to design a training strategy to approximate the diffeomorphism. Okay, from now on we will work with controls that are in L2. Okay, good. So we are given, actually we are not given a diffeomorphism psi with a topic to the identity, and we want to approximate psi on a compact set K. Okay, our approximation will be data driven. So we may imagine to observe the action of psi on an ensemble of points belonging to K. And with these are the initial ensemble, and with the observation we construct the target ensemble. Okay, what is the first idea that we may come up with? Okay, the idea is that, okay, we could use the exact controllability for finite ensembles. So there exists an admissible control U bar M such that the corresponding flow replicates exactly the action of the observed diffeomorphism psi. Okay, we achieve a null training error, this is true, but this is not a good idea. There are a lot of drawbacks in doing that. For instance, maybe we are also learning the error, if any, if some error is affecting our measurement. Okay, so from the machine learning point of view, we can say that the null training error strategy, with this poor strategy, we cannot provide estimates for the generalization error. From the mathematical viewpoint, the problem is that we have no control on the Lipschitz constant of the approximating diffeomorphism. So we are doing very well on the interpolation point, but the Lipschitz constant is exploding, and so we have no control on what is happening just outside the training points. Okay, change of paradigm, what happens? The answer, the Deus ex machina is the regularization. Okay, what does it mean? We introduce an L2, a penalization on the L2 norm of the controls, and hence the training process is to find an admissible control that balances these two quantities. This is the classical training error, mean squared training error, for example, and the second term is the L2 norm or the L2 norm squared of the control, and we want to minimize that. Okay, before with the poor training strategy, we had just a controllability problem. Now this is an optimal control problem. Basically, you can call optimal control problem whenever you have a function to be minimized on the space of admissible controls. Okay, so now the next step in order to provide actually an estimate of the generalization error is to prove a stability result. Gamma convergence is a tool from calculus of variations. It's not important that you know what it is. It's essentially a way to prove actually what I was saying, the stability result. So let's imagine that we provide our approximation with 1 billion points, and then we repeat that with 1 billion and 1 point. Everyone would expect that the two approximations would agree. Okay, this is exactly, this gamma convergence result will formalize this intuition. Okay, so in order to do that, let's assume that our points where we observe the diffeomorphism are sampled using a probability measure distributed on K. Okay, we construct the empirical probability measure, and we can rewrite the functional in this way. So this is exactly the same functional as before. I just replaced the sum, so the sum of the mean squared error, with this integral with respect to this empirical probability measure. Okay, what is the gamma convergence result is that the problem of minimizing Fm is gamma converging to the problem of minimizing F infinity, which is where this last function has exactly the same structure as the function Fm, but the integral cost is made with respect to the probability measure mu that essentially generates the data on T. Okay, what's the point? The main consequence is that the minimizers of the functional Fm are converging to the minimizers of the functional F infinity. So that's why if we repeat the approximation with 1 billion point and 1 billion point and 1, we are basically observing the same result. Okay, this is maybe a most important consequence is that the upper bound on the expected generalization error. This is a direct consequence of this gamma convergence. Okay, can be bounded by these terms. Okay, so we have a strategy. So the strategy is to minimize FM. We have understood that there are good reasons to do that. Okay, we just need a practical implementation to do that. Essentially, there are two possibilities. The first one is to follow a gradient flow strategy. Essentially, the functional FM induces a gradient flow on the space of admissible controls. And the second approach, which is for some aspect quite similar, is to use numerical methods based on the Pontegalian maximum principle. Okay, not entering into the details, but I'm just telling you that the construction of the ResNet takes place exactly now. Because if you want to discretize this problem solving it numerically, you have to discretize the control system, but whenever you discretize your control system, for instance with the explicit Euler scheme, you end up exactly with the ResNet. And thence solving the optimal control problem is perfectly equivalent to solving to training the ResNet. Okay, so yes, here I use the average notation for the linear control systems. Okay, possible application, normalizing flows. Okay, what are normalizing flows? So essentially, we can imagine to be given a random variable x with an easy distribution. Okay, a random variable in RD. Easy distribution, what does it mean in our framework? Means that it is cheaper to sample from x. Okay, on the other hand, we are also given a random variable y with a complicated distribution, and still by complicated I mean that it's expensive to sample from y. Or maybe we do not know actually the distribution of y, if you prefer. Okay, what is the task? The task is to find a mapping, possibly a diffeomorphism, that such that the composition T of x is distributed as y. If you manage to do that, essentially we can sample from y at a cheap cost, because we can just sample from x, compose with t, and actually we are consequently we are sampling from y. Okay, what is the idea? The idea is to try to use the machinery developed so far in order to accomplish this task. Essentially, this is a sort of a generative model, if you like, if you prefer to use this nomenclature. Okay, this problem is the problem of finding such mappings is well studied in optimal transportation. Okay, caveat, so far we have dealt with optimal control. This is optimal transportation. Both optimal, but the subject is rather different. Anyway, okay, what's the problem? The problem is that finding explicitly optimal transport map or just transport maps is in general very difficult. Okay, so same notations as before. So we have an admissible control, and with the admissible controls we consider the corresponding flow. What is the task? Okay, so we are given two probability measures, mu and nu, absolutely continuous with respect to RD. So before I talked about random variables, so we are now think it's better to think about their distribution rather than the random variable themselves. Okay, absolutely continuous with respect to the that measure with compact support, and we would like to make as small as possible this quantity. This quantity is essentially the Wasserstein distance between the transformation of mu through the flow and d mu. What does it mean? Okay, if you don't know what is the Wasserstein distance, it's not important. It's a way to quantify the distances between two probability measures. Okay, once again, our approximation will be data-driven. Okay, what does it mean? What are the data in these cases? Okay, the data are the empirical probability measures obtained by sampling from the two probability measures. Okay, I just want to stress that sampling from mu is cheap. So if needed, we can enlarge our data set in our empirical probability measure mu m, while sampling from mu m is extremely costly, or we cannot have further data. Okay, what is the difficulty? The further difficulty with respect to the previous stage of the diffeomorphism approximation, well, we have no correspondence assigned between the elements of the first, between the atoms of the first measure and the atoms of the second measure. Okay, so the idea, as before, essentially is to set up a variational problem, a minimization problem on the space of admissible controls. Okay, here I just repeated the notations. Okay, what is the task? The task is to make as small as possible the distance between the transformation of mu and the mu. Okay, essentially by using basic triangular inequality with the Wasserstein distance, we can decompose this quantity that in general will be difficult to measure into three terms. Okay, the first term is the distance between the empirical measure μm and mu amplified by the Lipschitz constant of the diffeomorphism constructed. So the first thing that we observe is that we should keep this Lipschitz constant bounded as before, after all. The second term is the most complicated and it is related to the training error, while the third term, we cannot act on it. It's a sort of gnoseologic limit. Okay, the overall, but it is very reasonable. So the approximation that we can hope to reach of the probability measure mu is strictly linked to the quality of the data that we are dealing with. So if the distance between the empirical version of mu and the nu is small, so we have a hope to produce a good approximation. If the distance is huge, we cannot. Okay, so okay, as I'm going to infinity, we may imagine that the distances between μm and mu and mu m and mu goes to 0. Okay, so what should happen? First of all, as I said, the Lipschitz constant of the diffeomorphism that we are going to produce should be uniformly bounded in M. Okay, and of course this means that we have to penalize the nth norm of UM, as done before. And the second term is the second term should be made as small as desired, uniformly in M. Okay, this term is the problematic one, and let's focus very briefly on that. Okay, in order to deal with this quantity, we should use a little bit the language of optimal transportation, but I don't want to enter into the details now. I'm just telling you that with quite basic computation in quite basic tools of optimal transportation, we can come up with this upper bound. So essentially, this Wasserstein distance can be approximated from above by this quantity. By this integral. Okay, the good news is that this integral is not actually an integral, but it is an integral done with respect to is essentially a sum. The probability measure gamma m is discrete, so this is not actually an integral; it's a sum. Okay, so essentially we end up with this upper bound. And we can basically construct, inspired by this one, we can construct the functional that we are going to minimize, which is this one, and essentially has a structure that is not so much different from the structure of the functional of the diffeomorphism approximation. Okay, what are the good news? The good news is that if the probability measure μm is weakly convergent to mu, and if μm is weakly convergent to mu, and this is important, the probability measure gamma m is an optimal transportation plan between μm and μm, then we have that the sequence gamma m is converging, the whole sequence without subsequences is converging to a probability measure gamma, which is an optimal transport plan between mu and mu, and which is induced by a map. Or if you don't know what does it mean, please ignore it. Okay, but this is a very good news. Okay, once again, okay, observations. The L2 norm of the minimizers of the functional Fm can be uniformly bounded from above with a constant that does not depend on m. And this is a very good news. It was exactly what we were looking for, to have a bound on the Lipschitz constant. And then once again we have a gamma convergence result, which as before is a stability result. Not entering into the details as before. We have the functional Fm and the corresponding gamma limit. Okay. Once again, what are the consequences of the gamma convergence result? The minimizers of the functional Fm are converging to the minimizers of the functional Fv, exactly as before. Okay? What is even more interesting is this inequality on how good is our approximation that we are providing. Okay? The quality of our approximation can be measured in terms of these three terms. Okay, the last one is once again is the same as before, our nosological limit. We cannot do anything on that. The first term is the Lipschitz constant that multiplies the distance between mu m and mu, and we have a bound on the Lipschitz constant L beta that depends on beta, of course. When beta goes to 0, the Lipschitz constant is exploding. And we have this term kappa beta. What is kappa beta? Kappa beta is linked to the training error, how small we can make the training error. And we would like to say that this training error goes to 0 when beta goes to 0. If it is the case, what we can do? Okay, we can choose beta such that this quantity is of the same order of this guy that we don't know. Okay, so this is as small as we desire. We end up with a huge Lipschitz constant, but this is not an issue because we can refine the measure mu m, we can reduce the distance between mu m and mu, and so we can make these two terms comparable. Okay? Is it true that kappa beta goes to 0 as beta goes to 0? The answer is yes, and in this case we needed some important and complicated tools of optimal transportation. It's a regularity result on the transportation map approved by De Filippis and Figalli in 2013. Okay, anyway, the point is that we managed to, okay, we have what we wanted. Okay, kappa beta goes to 0 as beta goes to 0, and we can manage the fact that L beta increases by refining the approximation of the probability measurement. Okay, now I have some pictures, some numerical experiments about the task of diffeomorphism approximation. The task of normalizing flow, we are still working on that. We hope to have the preprint available in a few weeks, but it's better not to do promises. Anyway, okay, what is that? The red dots are the original ensemble of points that we have generated that have been transformed by an unknown diffeomorphism psi, and the blue dots are the transformed points. Okay, so what happens? We used the maximum principal algorithm to train the ResNet. We used M600 training points and 128 inner layers. Okay, and essentially it turns out that this is the approximation provided in the training phase. So essentially the blue dots were the target points, and the red dots now are the transformation of the initial points through our flow. Okay, this is the training, the behavior on the training set, and this is the behavior on the testing set. Actually, we can observe that the approximation is very good. We have a larger density of data, as it's natural to observe, while we observe more errors where the data are less dense. Okay, so I think that is all.
Okay, so anyone has any questions for?
Yeah. Oh, thank you very much for the talk, very interesting. Just a curiosity, if you can expand a bit more, especially in the first part, so the approximation of the diffeomorphism, how can you use the gamma convergence result to prove generalization estimates?
Yes. Essentially, okay. Okay, what is the point? Okay, the point is quite delicate here, because the gamma convergence result is made with respect to the weak topology of L2. Because if we work with the strong topology of L2, the functional is not equicoercive. Actually, it's neither coercive. Okay, but what happens? You cannot do gamma convergence with the weak topology of L2 because it's not first countable, it's not memorizable. So what do? You prove a priori the fact that the minimizers of all the FM are uniformly bounded. So it's not restrictive to work on a bounded ball of L2 with the weak topology, but this time it is memorizable. And so we can work with the gamma convergence. Okay, what happens? I have for the fundamental theorem of gamma convergence, I have that the value of the minimizer of the minima are converging in value. The minimum is converging as m goes to infinity. The minimum value of this guy is converging as m goes to infinity to the minimum value of this guy. Okay. On the other hand, for the fact that I told you at the beginning, the magic is that weakly convergent controls are transformed into strongly convergent with respect to the C0 norma flows. So this guy is converging to this guy, and this is actually enough for the generalization error. But the fact that the minimum of this guy is converging to the minimum of this guy, this term is converging to the minimum of this term is converging to this term, implies that the norms of the minimizers are converging to the norm of this minimizer. So you have weak convergence plus convergence of the norms implies strong convergence. Anyway, this last fact is not so crucial for your question. Okay, this essentially follows from the fact that this term is converging to this term when evaluated on the minimizer. And I was quite fast in that in explaining this one. Okay, how can you actually obtain this term? Essentially by the triangular inequality. So you know from the result of my supervisor, from the controllability result, that you can replicate these you can approximate as precisely as you want these the diffeomorphism at psi k. So this term can be made as small as possible. Okay, and so the point is to choose the parameter beta small enough such that it is convenient to make these small. Okay, the price that you pay for that is that you may end up with a huge constant here. But at the end, as in the other case, if this is huge, you can just increase the basis and distance. Sorry, it was longer the answer.
Thank you very much.
There is a question over there.
Yeah, I have a couple of questions. So you have talked about the regularization on the U term.
Yes.
That is basically a regularization on the weight of the network.
Can you speak back?
Can you come here?
So you're talking about a regularization term, head to regularization.
This one for
Okay,
instance.
beta over 2.
Yeah.
Okay. And U is the parameters of the network, right?
Yes, that's right.
Yes.
You in the continuous time limit, so in the control system, but yes, yeah, the counterpart of the.
Okay, in the computational part of this, U are the weights of the network.
Yes.
And it's more like a suggestion because when you compute this and you try to solve this problem with neural network, the weights are also limited, or there are other regularization terms, like for example batch normalization, renormalization. So maybe you can try to consider different norms
Yeah.
in L2 and use this regularization that you can enforce in the parameter of the network
Yeah, of course.
for the abstract results, but also to study the convergence and the impact factor of this U, this regularization U on the convergence of the neural network.
Okay. Yeah, the answer is that okay, from the analytical point of view, using the L2 normal regularization is very perfect, nice, because you can work in an interspace. You have a lot of nice properties. But of course, it makes perfectly sense to consider other regularization term. It's something that should be done. For instance, I think that I'm going to do is to remove the regularization and to consider controls that live in a ball of NP.
Yes.
And to increase, actually the theory should be essentially the same, because the Wickstad topology of infinity has the same nice property of the Wick topology of L2, so on and so forth. And to increase the radius of this ball in an infinity in order to match to obtain the training precision or the validation precision that I need. No. Okay. No, yes. And also it would make sense to consider also L2, L1 regularization, because I don't stress that point, but what is crucial here is the choice of this family of controlled vector fields. Okay, I know that for theoretical reason I have to put inside these guys, but actually if I just use these guys, the results are not so good. What I should do is to add also the Lie bracket of these guys. And how many do you put? This is empirical, but if you add an L1 penalization, then essentially you are enforcing sparsity, and you are, for instance, counting how many are turned on. You can actually deduce what are the vector fields that are actually important to everything.
And another observation, you are using only the last step of the evolution.
The last step? Yeah.
You are
the
ResNet as a dynamical system.
Yeah,
but you are using only the last line of the
exactly right.
And maybe you can use, for example, a reinforcement learning strategy, and you can consider the time step of all the evolution, and not only consider the L2 term of the last step, but also all the intermediate steps.
No. The L2 norm is penalized. The L2 norm is the integral of okay. No. It's not of the last. Where is it? Okay. The L2 is an integral done on the evolution time. So if the L2 norm of the control.
Yes, but the first term.
The first term is just the final.
Yes, the target distribution and the end distribution that you are observing after passing all the data through the network.
Yeah.
But the intermediate layer of the network you are not using, but you can do this.
Okay.
And maybe you can add other terms
Okay.
for the intermediate layers and using a extra.
Okay. So, are we done? There was another guy that wanted to make a question. Another one, okay. So no, not you. No. Okay. So we really need to ask you what is the question. No pressure.
Actually, you cannot answer that. But I have another question.
Okay.
Could you please go back to the optimal transport
Optimal
slides?
transport?
Yeah, because I missed something. What is beta in that case exactly?
As before, is the weight on the L2, the parameter that weights. Okay. Here is the parameter that weights the L2 normal regularization.
Okay.
Exactly as before.
Okay. Okay. So and then you said that you can take it so that Well, you can minimize the distance, the losses and distance between the distribution and the empirical version, right? Because you can sample more.
Yeah.
From
This one.
from the first distribution from you.
Where is it? Yes, this one. This one can be essentially made as small as possible. Of course, it is all the training becomes more heavy, and there will be a trade-off also in that one. But in principle, yes.
And how is it the convergence of the distance in terms of M?
Okay. This is a very good question. At the beginning, we were not so smart, and so we were basically just sampling from the probability measure mu. But the point is that if you already know mu, if you, for instance, know its density, there is no point in sampling from mu and waiting to have a good approximation. It's better to construct, for instance, a uniform triangulation of your domain, a triangulation in terms of evaluation point, and put the mass on the evaluation point on the atoms of mu m proportionally to the density of your distribution. In that case, with a much smaller m, you can achieve a very good masses and
So you are sure to cover the.
Yeah, we are working with, for technical reason, the result of Fidari and the Philippines works with the compactly supported probability measure. So you can actually the mu for in our experiment, in our partial experiments that we have, is a uniform distribution over a circle. It's not a Gaussian. It's better to use a uniform rather than a Gaussian because it's more for our academic purposes, of course, not for real life applications.
Okay, and just so no, this is just a curious suggestion because here your mu is a reference distribution,
Yes.
right? So one suggestion is actually you can try some estimates of Stein's method, where basically since you already know mu, don't sample, and basically you coalesce the first two terms. You basically have computing any Wasserstein metric or Kolmogorov metric, mu with the new m. So you basically sample from the costly distribution because you already know the reference distribution, right? And you want to see from the samples of the costly distribution how close it corresponds to your reference distribution in an optimal control problem. So you can get, I think, good estimates by using some already known techniques in Stein's method.
Yeah, but the fact is that what is done actually in the problem of normalizing flows is to take the reference measure and transform it to the flows, so through the ResNet. The problem, and then you perform actually a maximum likelihood estimation based on the observation, so based on UN. So you maximize the parameters of your ResNet in order to obtain a maximum likelihood flavor of we would like to provide a more, let me say, variational approach. But I'm not saying that this is better than the I think that probably.
Any other question? Oh, sorry.
Okay.
Okay, so let's thank the speaker once again.